So good morning, everyone. I'm sorry that we're not seeing each other, quote unquote, virtually. So the first thing I want to do for the lesson for today is we did page 1. I gave this as an attachment. This was a review of some topics from chapters 7 through 9, and we did page 1 last week together. So what I'd like to do is go over some problems on page 2. Again, this is still topics from chapter 7. So the first problem, problem number 4, is going back over integration when you have to do your partial fraction decomposition. Remember, one way to recognize that you may have to do a partial fraction decomposition is when you have a rational function where u sub does not work and the trig, your inverse trig, doesn't work. Another recognizable thing is that you can factor the denominator to help you do that particular u sub. So first thing we're going to do is when we take a look and we can see that a u sub's not going to work. I'm just going to try and fix the focusing here. It looks just a little blurry, so give me just a second. See if this is any better. Yeah, okay. So first thing I'm going to do is I'm just going to factor, and I have a separate sheet of paper because I really don't have a lot of room to work on this worksheet. So I have 5x minus 5 over 3x squared minus 8x minus 3, and I should have a dx there. So the first thing I want to do, again in problem number 4, is I'm going to factor the denominator. So when I factor the denominator, that's going to give me x minus 3 times 3x plus 1 dx. Again, we just double check. I have a 3x squared minus 9x plus 1x is a minus 8x and a minus 3. So what we want to do is we want to, remember, take this larger rational expression and split it up into 2 smaller fractions. So what I'm going to do first of all is I'm going to take my fraction 5x minus 5 over x minus 3 times 3x plus 1. And again, because both factors in the denominator are linear, I'm going to have one factor be the denominator of one of my partial fractions. I'm going to take my second factor, and that's going to be the denominator of my second fraction. Since both these factors are linear, remember we're only dealing with proper fractions, which means that the numerator has to be 1 degree less. So I know for both of these fractions, my numerators are going to have to be constants. So I'm going to call that a and b. So now what I'm going to do is multiply this entire expression by the LCD to clear the fractions out of this equation. So I'm just going to be left with 5x minus 5 equals a times 3x plus 1 plus b times x minus 3. And that's where we're going to use that finger side method or cover-up method. So the first thing I'm going to do is I'm going to let x be equal to 3. Again, that's the 0 coming from this particular factor. So I need to plug 3 into this entire expression wherever I see an x. So 5 times 3 is 15, 15 minus 5 is 10, equals 3 times 3 is 9, 9 plus 1 is 10, so I have a 10a. And of course that's going to go to 0. So I know that a is equal to 1. So now the 0 that comes from this particular factor is going to be negative 1/3. So I'm going to let x be equal to negative 1/3. So I have to plug negative 1/3 into this side of the equation for x. So 5 times negative 1/3 is a negative 5/3 minus 5 equals, again, I know that's going to go to 0, and then negative 1/3 minus 3. Again, negative 1/3 minus 9/3 is going to give me negative 10/3 b. So then when I subtract negative 5/3 minus 15/3, that's going to give me negative 20/3. So to solve for b, I'm going to multiply both sides by the reciprocal. So I'm going to multiply both sides by negative 3 over 10. So b is going to be equal to 2. So now I know what these two fractions are going to look like. I know now I can rewrite my integral as the integral of 1 over x minus 3 dx plus, and I'm just going to go ahead and split my integral. Again, plug in my 2 for b, 2 over 3x plus 1 dx. And I'm going to go ahead and integrate. Again, so my integral of 1 over x minus 3 I know is the natural log of the absolute value of x minus 3. Plus, now if you take a look at this integral right here, I can pull the constant of 2 out. And notice in this denominator I have a 3x plus 1. So I'm going to have to do a u sub. So u is equal to 3x plus 1. My du is equal to 3 dx. So what I'm going to have to do is divide a 3 out of this particular integral. So I have 2/3 times my integral of 1 over u du. So then I know that this particular integration is going to be 2/3 times the absolute natural log of the absolute value. Again, replace u with that 3x plus 1. So I plus 2/3 times the natural log of the absolute value of 3x plus 1, and don't forget to add your c because you have the improper integral. Again, don't ever forget when you're dealing with this partial fraction that you have to split up, use your properties of integrals, separate the integrals, because again, you don't want to accidentally pull that 2 out and have it apply to this first integral and have 2 ln of x minus 3. So just be careful with those constants. So then the next question is another problem where they put a spin on doing, this was a multiple choice from an AP exam a couple years ago. When p is between 0 and 100, which of the following is an antiderivative of 1 divided by 100p minus p squared? Again, I'm just going to recopy this. So again, they want me to find the antiderivative, so I'm going to have to integrate 1 over 100p minus p squared dp. Again, looking at the integration techniques, you can factor this denominator. So I can rewrite this as 1 over, I can factor out a p, that's going to give me 100 minus p dp. So I need to do my partial fraction decomposition, so 1 over p times 100 minus p is equal to, again, one of my factors is a p, so that's one of my denominators. 100 minus p is my other factor, so that'll be my second denominator. Both of these factors are linear, so I know my numerators are constant, so I'm going to call this an a and this a b. So I'm going to multiply this entire equation by my LCD of p times 100 minus p. So that's going to give me 1 is equal to a times 100 minus p plus bp. So I'm going to let p be equal to 100. So again, when I plug in 100, I have 1 is equal to 100b. So b is equal to 1 over 100. My other factor is going to be, I'm going to let p be equal to 0. So I have 1 is equal to 100a. So a is equal to 1 over 100. So then I can rewrite this particular integral, since I know that a is 1 over 100, b is equal to 1 over 100. I can rewrite this integral as my integral of 1 over 100 over p plus my integral of 1 over 100 over 100 minus p. I can pull out this constant. So that's going to give me 1 over 100 times the natural log of the absolute value of p plus. Now right here, I know I can pull out this constant, but because this denominator is 100 minus p, I have to do a u sub. U is equal to 100 minus p, du is equal to negative dp. So I have to pull out a negative 1 over 100. So negative 1 over 100 times the ln of the absolute value of 100 minus p plus c. Sorry, that got a little squished there. So my final answer would be 1 over 100 natural log of the absolute value of p plus negative 1 over 100 times the natural log of 100 minus p, and again, don't forget to add your c. So just to review that, that integration by your partial fraction decomposition. So last topic on this page that I wanted to make sure I addressed with you was improper integrals. Remember, improper integrals is when your upper bound or lower bound are plus or minus infinity, or it could be undefined at your bounds or between your upper and lower bounds. So for example, you may have one of your bounds be positive infinity, and remember what we did was you're going to take the infinity out and replace it with a b, and what we're going to do is we're going to find the limit as b approaches infinity. Remember, it converges if the limit exists, it diverges if it does not. Your lower bound may be negative infinity, so we're just going to then again replace negative infinity with an a, and we're going to find the limit as a approaches negative infinity. Remember, if your bounds are both infinity and negative infinity, you split it at some constant. You have to split the integral. Again, split it at c. The easiest place to split it is 0, as long as the integral is not undefined at 0. So for example, let's take a look at 6a. So 6a, notice you have your bounds of negative infinity to positive infinity. So what I'm going to do, first of all, is I'm going to, again, you can split it first or recognize that this is going to be a u sub problem. Notice what's underneath the square root is 2 plus x squared. I know the derivative of this would be a 2x, so I know that this is going to be a u sub. So I could just go ahead and rewrite this as a u sub first. So u is equal to 2 plus x squared. My du is going to be a 2x dx. So I know I can rewrite this integral as 1/2 times my integral negative infinity to positive infinity of u to the negative 1/2 du. So what I'm going to have to do is I'm going to have to split my integral. Again, I'm going to go ahead and I'm going to split it at 0. So I have 1/2 times my integral of negative infinity to 0 of u to the negative 1/2 du plus 1/2 times my integral from 0 to infinity of u to the negative 1/2 du. So now remember, once you do your integration, what happens here is, remember, as long as if one of these diverges, the whole thing is going to diverge. So I can rewrite this replacing that negative infinity. So I'm going to have 1/2 times the limit as a goes to negative infinity, going from a to 0 of u to the negative 1/2 du, plus, now I've got 1/2, and again I'm going to replace infinity with b, the limit as b goes to positive infinity, going from 0 to b of u to the negative 1/2 du. So now what I'm going to do is I'm going to integrate. So again, when I integrate u to the negative 1/2, I know that's going to give me 2u to the 1/2, and 1/2 times 1/2 will give me a positive 1. So this is just going to give me the limit as a goes to negative infinity of u to the 1/2. And again, I'm going to have to evaluate this from a to 0, plus the limit as b goes to infinity of u to the 1/2. Again, this is going to go from 0 to infinity. So again, I know u is 2 plus x squared. I'm just replacing that u with that 2 plus x squared. And again, dividing this from a to 0, and this from 0 to infinity. So I'm just going to take a look. Like I said, if one of these diverges, the whole thing's going to diverge. So I'm going to take a look at this limit as b approaches infinity of 2 plus x squared to the 1/2. So if I take a look at the limit as b approaches infinity, as x is getting larger and larger and larger, I'm not approaching a fixed number. The behavior of this function is approaching infinity. So since this is approaching infinity, we can say that this whole entire integral diverges. So I don't even need to worry about calculating the limit of this particular one. So that's how, remember, when you're dealing with an improper integral where your bounds are negative infinity and positive infinity. Now let's take a look. I'm just going to get out a separate sheet of paper here. since I used up, let's take 6b. So 6b, I've got my integral from 0 to 4 dx of the square root of 4 minus x. Now, what makes this an improper integral is because if you notice your upper bound of 4, 4 is where this is going to be undefined. So when you have one of your bounds where it's undefined, again, what we're doing is think about what your integral is. It's the area under the curve. So what I want to do is I want to calculate the limit as b approaches 4 just to the left of 4. Because again, when we talk about the left of 4, we're talking about those values slightly smaller than 4. So I can rewrite this from 0 to b of 1 over the square root of 4 minus x dx. Again, I'm going to do a u sum. U is equal to 4 minus x. My du is negative dx. So I'm going to pull a negative sign out. So I have the limit, and again I'm going to put my negative sign right here, as b approaches 4 from the left, from 0 to b, and I'm going to rewrite this as u to the negative 1/2 du. So when I integrate, this is going to give me, when I add 1 to 1, that's going to give me a negative 2u to the 1/2. And again, I'm evaluating this from 0 to b, and I need to find the limit as b approaches 4 from the left. So then I can replace u with the 4 minus x. So I'm trying to find the limit as b approaches 4 from the left of negative 2 times 4 minus x to the 1/2. And again, I'm evaluating this from 0 to b. So by my fundamental theorem of calculus, I'm going to plug in my upper bound. So I find the limit as b approaches 4 from the left of negative 2 times 4 minus x to the 1/2. Again, I'm plugging in that b, minus the limit as b approaches 4 from the left of negative 2 times 4 minus 0 to the 1/2. Well, when I do a direct substitution, I'm plugging in a 4. 4 minus 4 gives me 0, so this is all going to be 0. Minus. So again, there is no b to plug in, so I'm just going to simplify. 4 minus 0 is 4. 4 to the 1/2 is 2. So I have negative 2 times 2, which is going to give me a negative 4. So 0 minus negative 4 is 4. So we would say that this particular interval, it converges, and it converges very close to 4. So again, I just wanted to make sure we did a little bit of review of those improper integrals. The FRQ reviews we've been doing, they occasionally have an improper integral in there, and I certainly would expect an improper integral question on your AP exam, so I want to make sure we went over those. You probably will see in your final exam reviews a couple multiple choice questions also reviewing this as well.